So this is the second lesson from the same section of the textbook. And really the focus of this is just a little bit more practice and a little bit more work with understanding the notation of what a limit is and how to visualize a limit. The actual algebraic process of determining limits without substitution we won't really get into until the next lesson. So still a large visual component to this. With that said, I want to first start by talking about a definition of a vertical asymptote. And really, the best definition of a vertical asymptote involves limits. And so if a function has a vertical asymptote at some point, and I said a, then just one of these, there's kind of 6 possibilities. Any one of these following can be true. If any one of these that I'm going to mention in a moment are true, then there's a vertical asymptote there. And so if there's a vertical asymptote when x approaches a, sorry, I should say, if there's a vertical asymptote when x equals a, then one of the possibilities is if we approach a from the left, the limit should be infinity. Or if we approach a from the left, the limit should be negative infinity, which means as we approach from the left, if the graph goes up forever or down forever, we have a vertical asymptote. We kind of really, again, this is nothing really new, it's just defining it using limits. So another possibility is if we approach a from the right. And again, if the limit equals infinity or negative infinity, we know there's a vertical asymptote there. And finally, if it approaches infinity, as we approach a from either direction, so a two-sided limit. Again, if the limit equals infinity or negative infinity, we have a vertical asymptote there. So if any one of these, if we know that any one of these 6 variations is true, then we know there's a vertical asymptote at a. If none of these 6 are true, then there's not a vertical asymptote at a. And so what I have here is a graph of this function, f of x, root x plus 2 over x times x minus 2 squared. The equation doesn't really matter. But here's the graph. And so I can see, for example, there must be a vertical asymptote at 0. And I can tell that from looking at the graph or from looking at the equation. When x equals 0, I'm dividing by 0. As well, I can tell there must be a vertical asymptote right here. But that's not labeled. But by looking at the equation, I know this must be negative 2. And so now I also have an endpoint right here. That's because when x is less than negative 2, my numerator is a non-real number. All right, so hence that kind of explains some characteristics of this graph. And again, this graph is all from this one equation right here. But that's it. Let's look at these 9 limits. And as usual, I'd recommend you pause this and try these before you watch much more or any more. But the limit as we approach 0, which means from the left and the right, I can see it's different. And from the left it's going down, from the right it's going up. So this does not exist. The limit as we approach 0 from just the left, though, is going to be negative infinity. The limit as we approach 0 from the right is positive infinity. All right, what if we approach 2? Well, again, if I just approach 2 from both sides, that's the first one, it's on both sides from the left and the right, it's approaching infinity. So this will equal infinity, this will equal infinity, and this will equal infinity. And finally, what about when I approach negative 2? Well, first of all, I'm going to do this in a reverse order. As I approach negative 2 from the, I feel like I have a typo here. Yes, I do. There we go. This last one should have a plus right here. There we go. So yeah, I do want to start from this one. So this means I approach 2 from the right. Looking at the graph, as I approach 2 from the right, this equals 0. As I approach negative 2 from the left, there's no function there, so the limit does not exist. And even though these 2 here are not the same, because negative 2 is an endpoint, when we say as we approach the limit as we approach negative 2, we say this still equals 0 because that's an endpoint, and we saw that last day. So like I said, nothing really new here. Really, I've defined a vertical asymptote involving limits, but we kind of informally saw that last day anyways. With that said, what if I ask you the same thing, but I don't give you a graph? And so what I want to do is I want to look at cosecant x. And the first thing I want to do is sketch a graph of cosecant. So I don't expect you to know immediately what cosecant looks like, but we should be able to visualize the basics. Cosecant is 1 over sine. And so what does 1 over sine look like? Well, again, I don't expect you to know immediately, but I do expect you to know what sine looks like, so let's focus on sine first. And sine I'll draw in red. Draw some key points on sine. And that's it. If I look at my values for my limits, so I know how far to draw a sine, I'm only going from 0 up to pi. So I've drawn more than enough here. So I'll just kind of, come back here, graph. Draw it this way, arrow this way. OK, so this is the graph, my quick little graph of sine. And again, I'll show that this is at -1, this is at +1, this is at pi over 2, this is at pi, this is at 3 pi over 2, and this is at 2 pi. All right, so what must cosecant look like? What must 1 divided by this look like? Well, first of all, it's 1 divided by sine. So anytime sine equals 0, I know I'm going to have a vertical asymptote, a pointed or I should say I know I'm going to have a discontinuity, but I know it's going to be a vertical asymptote, not a pointed discontinuity, because it's just 1 in the numerator. It's not like sine is dividing by itself. So I know that cosecant is going to have a vertical asymptote everywhere sine equals 0. And there's others over here. We get the idea. So everywhere sine equals 0, I have a vertical asymptote. OK, what else do I know? It's just 1 divided by sine. So everywhere sine is positive, like right here, in this region where sine is positive, the outputs are positive, 1 divided by a positive number is still going to be positive. So I know in that region between 0 and pi, I know cosecant is going to be positive. Whereas the opposite is true right here. In this region, where sine is negative, where my outputs are negative, 1 divided by a negative number is going to be negative. So I know in that region, between pi and 2 pi, cosecant is going to be all negative. And again, this repeats. So once I understand these two regions, I can kind of continue it onwards. What else do I know? Well, when sine equals 1, at this point right here, when sine equals 1, 1 divided by 1 is 1. So I know that cosecant is going to go right through that point. And I know that cosecant is also going to go right through that point right there at -1, because 1 divided by -1 is -1. And other than that, I know the closer I get to one of these asymptotes, the more that cosecant will get either towards infinity or -infinity. Well, again, I already know that in this region here, cosecant's positive, and I know it goes to this point here. And I know as it approaches either of these asymptotes, it's going to get, therefore, closer to positive infinity. So already I can kind of visualize what this must look like. This must look something like this. Which means also over here, that must look something like that. And over here, we must have something like that, where all of these points, the lowest point's at 1. And then when sine is negative, it must be kind of the reflection of that. So like this, or like this, and so on, where these points here are at -1. And so what I've sketched in green is the graph of cosecant of x. And all relied on knowing what sine looks like, relied on understanding why we have vertical asymptotes. That's when I'm dividing by 0. And also these points where sine is 1 or -1, because again, 1 divided by 1 is 1, 1 divided by -1 is -1. So at those places, the two graphs should be invariant, should be the same as one another. OK, with that said, now I have a sketch that I can use to answer all these questions. And so the limit as I approach 0 from the left of cosecant, again, all this is about cosecant. As I approach 0 from the left, it's -infinity. As I approach 0 from the right, it's positive infinity. So the limit as I approach 0 does not exist, because they're not the same. This function has no endpoints. Cosecant, well, sine has no endpoints, so cosecant has no endpoints. And so if my two limits from the left and right aren't the same, I know my limit will not exist. OK, what as I approach pi over 2? As I approach from the left, it equals 1. As I approach from the right, it equals 1. So as I approach pi over 2, it equals 1. And finally, when I approach pi, which I can just see on my graph, as I approach from the left, it equals positive infinity. As I approach from the right, it's -infinity. And therefore, they're not the same, does not exist. So really, most of my work here was visualizing the basics of the graph of cosecant. And we should be able to do this for any of our reciprocal functions. Just get a basic graph. All right, so the last question, maybe it looks a bit daunting. The last question is I give us a whole bunch of characteristics of a function with mostly limits, but not all limits. And we want to think about what the graph must look like. It's kind of reverse. A lot of the questions I've given you lately, I give you a graph, and you want to answer various questions. What's the limit at various points? This is the other way around. And so what must this graph look like? So we want to sketch a possible function for y equals f of x that has all these conditions. And as it's probably not surprising for me to say, it's not terribly hard to find a few of these, but it's going to be most likely challenging to find a graph that fulfills all of these. So f at -5 has to equal 0. The limit as x approaches 0 does not exist. The limit as we approach 0 from the left is infinity. As we approach 0 from the right is -1. The limit as we approach 1 equals 0. F at 1 is 1. The limit as we approach 3 is -infinity. And f at 5 is 0. All right. So really, in a moment, I'm just going to work through this and show you a basic variation of what this must look like. But I highly, highly, highly recommend you spend some time on this on your own. Just watching me do it is kind of a waste of time. I would definitely try this on your own. You'll probably make a few mistakes, but that is so much more valuable than just watching me do this. Because in a moment, I'm just going to basically show you an answer. All right. So let me set up my x and y axes. The basic idea, if you want to try this, is try sketching some things out, definitely in pencil, and then be willing to make adjustments. A few things I can see right away. If I look right here, the limit as we approach 0 from the left is infinity. The limit as we approach 3 from both sides is -infinity. So I know there's asymptotes at 0 and 3. So I know there's an asymptote at 0. I'll draw that right here. And at 3, which I don't know, I'll call it right here. OK, so I know there's vertical asymptotes there. The asymptote at 3 is -infinity, and it's a two-sided asymptote. So I know from both sides, the left and the right, it must be approaching -infinity. So I know it's going down this way, it's going down this way. All right. Whereas this limit right here, it's only approaching infinity from the left. So I know it must be going up like this. All right, so I've already got a fair number of details done. I know the limit as we approach 0 does not exist, but that's not surprising because I can see right here the limit as we approach 0 from the right is -1. And so because these two are not the same, honestly, I don't really need to tell you that. So I can now show that as I approach 0 from the right, it's approaching -1. So I'll look at my y-axis. Let's call -1 like right here. And I know it approaches here. What I don't know yet is if it approaches from the top or from the bottom. I don't know which way it's coming. But I do know right here that f at 1 is 1. But I know the limit as we approach 1 is 0. OK, how can all this be true? So if f at 1 is 1, but the limit as we approach 1 is 0, that means I know my graph from both sides. Because again, if you look right here, this is a two-sided limit, which means from both the left and the right as we approach 1, my graph is going to approach 0, which is the x-axis. So I know my graph must look something like this from the left, like this from the right, but it must have an open point right here. How do I know it has an open point right there? Because right here, f at 1 is 1, not 0. So I know it must be a closed point up here somewhere. And now I can start to piece together other parts of my graph. I know this must go down like this, and I know this must approach 1 like this, because don't forget I said right here. The limit as we approach 1 is, oh, sorry, wrong one. I'm getting so messy here. This one right here. The limit as we approach 0 from the right is -1. Now, what else do we have here? I know that f at 5 is 0. So f at 5 is 0. That means when x is 5, the output is 0. So I'll kind of show that right here. And I know that's on a limit. That's the actual value of the function at 5. So I can put a closed point there. I know also right here f at -5 is 0. So same idea over here. -5, put a filled in point. And I've got this point, everything taken care of. I think every point here I've taken into account. So all that's left now is, there's no specifications about the domain. So honestly, I could actually just have my function stop here, like this. But that's it. I might as well just kind of connect these. And before I go on, let me erase all of this and just double check that everything's correct. Now, to be honest, I know it is, but this is what you'd want to then do, is just double check. There's a lot of characteristics. Is f at -5 0? Yeah. Does the limit as we approach 0 not exist? Yes, because it's different from the left and the right. The limit as we approach 0 from the left is infinity. The limit as we approach 0 from the right is -1. I can see that. The limit as we approach 1 from either side is 0. Yep. But f at 1 is 1. That's what that point right there is. Yep. The limit as we approach 3 from either side is -infinity. And f at 5 is 0. So all I'll do is just make my marker a bit bigger, kind of draw this a bit darker. That's it. There's lots of variations you could have. For example, I'm showing my function stop at -5. It could keep going. Nothing about this says -5 is an endpoint. Plus, I'm drawing fairly simple curves here. How do I know it doesn't do stuff like this? Well, I don't, but why do that? But again, that's I'm just keeping it as simple as possible. As for f at 0, I have an open point there, f at 0. If I look at all my choices here, nowhere here does it say that f at 0 is defined or not. So I could leave it open. I could shade it in as well. It would make no difference. Because again, none of my characteristics involve that. Again, lots of possibilities, but all the correct possibilities should have a whole bunch of things in common. So before I end this lesson, this idea here of using all these limits to visualize a graph gets really, really important for a later part of the course, one of the hardest parts of the course, which is using derivatives, and which we haven't really learned about yet, to visualize the behavior of really complex functions. And questions like this are actually a really great lead into that. So expect to find these a bit challenging, but also expect us to try some things, use an eraser, make some changes, and keep double checking your constraints. But that's all. So I'm going to stop.